Welcome to Area Under the Curve and the Spinning Wheel of Death, apparently. Um, we're going on without me. This is 1/6, and we were looking at graphing motion and how to understand what's happening without actually seeing the thing move, but instead looking at something like this. So consider this. This is a velocity, and this is time, right? Meters per second and second. You put this in your notes, maybe sketch this. Uh, if you were going, say, this is 5 meters per second, and you went for 1 second, how far have you gone? In 5 meters per second for 1 second. Oh, 5 meters. What if you went for 10 seconds, right? Or let's just make it easier, 2. 5 meters per second for 2 seconds, right? The first second you go 5 meters. The second you go 5 more, that's 10. If you went for 3 seconds, that's 15. 5 the second, first, second, 10 the second, and 15 the third. And in fact, right, you just keep adding 5 every second that goes by. And instead of adding a whole bunch, if we want to add a whole bunch, we can save ourselves the trouble and multiply. And when you do that, you'll see, like, if you went for 10 seconds, instead of adding a whole bunch, you could say, oh, this length is 10 seconds. And I'm going 1, 2, 3, 4, 5 blocks. 5 by 10 is 50. And that's the distance we traveled in that time. Right? You could play the same game without counting for 2 seconds, right? How if you go 5 meters per second for 2 seconds, you should go 10 meters. One way you can do that is say, oh, 2 by 5 on a velocity curve gives you a distance of 10, right? 10 meters. So the area in some cases means something, has some significance. And even when it's not a straight line, you could do that. You started from 0, and at 10 seconds you were going 5 meters per second. One way you could think about it is you're averaging 2.5 meters per second over 10 seconds. You could cut this into like a box, right, and put half of it up and half it down. Or you could think about it as this same box as this first example, but we only have half of it, so we've gone half the distance, which makes sense because you're averaging not 5 meters per second, but 2.5 meters per second over the whole time. So you can break this up with just some geometry, right, and look at the area under the curve that way. As our curves change to actual curves, then you use calculus, and you'll have to wait for that. That's a little more fun. But we want to be able to break this up geometrically. So I know we're going rise over run, but the area under a curve in a velocity time graph is position. You should have that in your notes. And also the area under a curve in in an acceleration versus time graph is velocity. And let me give you some units. We'll give you some units in a second to show you why. Okay, but let's give it a shot. Here's a little hand-drawn sketch. You're going at 4 meters per second for 5 seconds. So 4, 8, and just keep adding or multiply them instead and say, hey, I've gone 20 meters. Okay, so here's the units behind it, right? If you go 4 meters per 1 second, and you multiply, that's this speed, and you multiply by, sorry, that's this speed, you multiply by this, which is 5 seconds, so we're multiplying by 5 seconds over 1, I suppose. Look what happens to your seconds. Gabam, gabam, and you're left with 20, and the units are just meters. So we know that's a distance, right? Neat how that works. All right, what about this? You're going negative 3 meters per second for 12 seconds. Find the area. Well, sounds like negative 36 meters. Cool. Think about this one. You're moving at a slow velocity, and then after 5 seconds, you pop to a high velocity, 3 and then 7. Right? Not a big deal. This is 3 by 5. This is 15 meters that you've moved during that first time. And during that second time, you've moved, well, it's not 12 seconds, but the difference between 5 and 7, 5 and 12 is 7. So for 7 seconds, you've moved 7 meters per second. Right? 7 meters per second. So 7 by 7 is 49. and you add that up, and those distances are summative, right? Means add them up. Neat. And so add those up to find the total distance that you've moved. Same thing if you have some negative and some positive. You're moving at 13 meters per second per 9 seconds. If you find the area there, oh, but then you stop, and now you move backwards. I know because it's a negative velocity. And from time 9 to time 15, right, that's 6 seconds. For 6 seconds, you move at negative 8 meters per second. That means you're moving backwards and burning some of this off. So you can take this area and subtract, remove this area, and see what's left over. And it's, in essence, for a while you're going positive direction, and then this is a smaller area, so for a little while you're going backwards, and when you subtract, the net is what you're left over with. Neat. You can try that with these as well. You're starting at 0, you end at 8 meters per second, which means you average 4 meters per second. So one way to do that is think average 4 meters per second over, what is that, 10 seconds? Alternately, you could think of just some geometry and say, oh, if I was going at a flat rate, this whole box is 80. It's 8 by 10. Right? So this whole thing is 80. I've only got half of it, so I've only gotten half of the distance, so 40 meters. 1/2 base times height. You can play the same game here by perhaps breaking this into a box and trying to find that area and then this area. Yeah. So this is 8 by 20, so 160. And in addition, because of your increasing velocity here, this is half as big as this whole box. So let's figure out this whole box and cut it in half. This is between 8 and 18, so this is a change of 10. This is a change of 20. So the whole box is 200. So half the box is 100. So we really have this total distance traveled. Oh yes, thanks, I wanted all of that. Me and Smartboard were fighting today. This is 260, that's the distance you've traveled. Okay, that's the basics. I'd like you to read through some of the examples and look at what's happening. Even if there's a curve, we can sort of approximate it by adding up boxes and approximating that. That's what we like. One of the reasons we like calculus is that it helps us actually find exactly the area under that curve without like breaking out a ruler and counting boxes. Again, try to figure out the height and the width on a velocity time graph. In a VT, velocity time graph, the height is going to be velocity, so meters per second. And when you multiply that by the width is time, right? So seconds, and the seconds cancel out your meters. The exact same thing goes if you're looking at an acceleration over time graph. The area can find you velocity. So if you drop something and the acceleration is 10 meters per second, and that happens for 5 seconds, we're going to call down positive, I guess. You can see how much velocity it has by looking at the area underneath. It's 10 by 5, it should be 50. And we could figure that out because this height right here is meters per second, right, squared. And if we multiply by time to get this area, right, we're multiplying this, which is just seconds, and meters over seconds squared times seconds over 1, this and one of these seconds and that seconds cancel, and you're left with meters per second. So 50 is the velocity, or speed, the magnitude thereof, right? So add those in there. Cool, here's a little summary in your notes. Make sure you're comfortable with gradient, area, that sort of thing. Slopes kind of go one way, give you displacement, slopes give you velocity, and then acceleration, and area goes backwards. One's differentiation in calculus, the other's integration. Get excited. And I'd like you to finish up anything from 17 to 19. We'll get back together and make sure everything's copacetic. Cool? See ya.